Speaker is Miklos Racz from Miklos Racz.
Thank you. Thank you all for coming, and thank you for the organizers for the invitation to speak. It's been a wonderful workshop. And what I think has been the best part of it is that we've seen excellent talks on a whole spectrum from theoretical to applied. And I think really this cross-pollination of ideas from theory and applications is very, very useful. And this is what leads to much of the progress. So what I'll be talking about is more theoretical, but I hope that some of the ideas and the questions studied will be of interest to a more broader audience. And this is joint work, based on joint work with wonderful collaborators, Sebastian Bubeck, Ronan Eldan, Elkanan Mosel, Jacob Ritchie, and Celil Sham, and we'll see various parts which are with various people. So what I'd like to talk about are networks that are out of equilibrium. There are many networks that are constantly evolving and which are not in equilibrium. There are many networks that are growing over time, and on top of that you could have edge deletions and all kinds of nodes leaving, many things. So many networks are out of equilibrium, and so a natural question to ask is, how does the time evolution of the network leave its mark on the structure of the network? So in particular, the types of questions I'd like to ask are, if we see a snapshot of the network now, a large network, what can we say about the past? Perhaps a past state far back in time. Can we say anything about it? You can think of this question in the forward sense as well. If you started some graph evolution, network evolution from some particular state, what mark does that leave on the current network structure? Okay? So this is the type of question I'd like to ask. And there's been all kinds of work on this, especially on the more applied side, so you can approach this problem from a variety of angles, from a data-driven point of view to looking at various simulations of trying to trace back your network, and so forth. So what I'd like to do is look at this problem from a more theoretical, statistical perspective and try to understand the basic fundamental statistical problems. And the two most fundamental statistical problems are those of detection and estimation. So detection is if we start from a particular initial graph, which we'll call a seed, can you detect the influence of that when you've grown the graph, the network, to be very large? Okay? And then the estimation problem is, so if you can detect the influence of the initial seed, the estimation problem is, well, can you estimate this seed? What can you say about it? Can you locate the initial seed in the large graph of interest? And so on. Okay? Are the basic questions clear? Okay, so a natural approach to studying these questions is to look at a bunch of generative models of randomly evolving networks and to understand these questions on them. So in particular, what we'll do is study some basic canonical models of randomly evolving graphs. In particular, we're going to, for simplicity, we're going to consider randomly growing graphs and look at these questions. Okay? And so we're going to really look at the most canonical models of randomly growing graphs, and for simplicity, we'll look at trees, because trees are simply simpler than graphs. But of course, the questions I'll be looking at are of interest more generally. Okay? So, well, in a randomly growing tree, there's some current tree, and then a new vertex comes in, and it attaches to some existing vertex according to some probabilistic rule. And the two most canonical models are preferential attachment and uniform attachment, which we've seen a lot throughout this week. So in preferential attachment, you pick a node with probability proportional to its degree. And in uniform attachment, you just pick an existing node uniformly at random. So I'm not claiming that these are necessarily good models for modeling realistic networks, but I do think that these are basic building blocks in many network evolution processes, and we've seen this throughout the week. For instance, if you recall Peter Orban's talk of a new model, a new random walk-based model for network formation, there he had two components. One was new vertices coming in and attaching to existing ones, and that was done exactly according to one of these two rules. And another was an edge creation mechanism, which was done according to random walk. Okay? So these are clearly important elements in network formation. More generally, you can consider other network evolution rules. You can attach with probability proportional to the degree raised to some power alpha, and these are special cases with alpha equals 1 and 0. And more generally, you can consider your favorite tree growth model or graph growth model and ask the questions I'm going to ask and study them. Okay? So if you have a graph evolution process, you can start from any particular initial condition, any particular initial graph, which in the case of trees will be an initial tree, which we'll call the seed. And the questions we want to ask are, how does the graph evolution depend on the initial seed? Okay? So let's look at some simulations to begin with. So let's run preferential attachment, and let's start it from either a star or a path of length 10. Okay? And if you run it until you have 500 nodes, it looks something like this. And you can see that this has some kind of star shape to it. And the central vertex, which is this initial center of the star, has a relatively large degree, so that here the area of the circle representing that vertex is proportional to its degree. Here at the bottom, you can see that this tree has some kind of path structure to it. Okay? So you can see the remnants of the initial seed in the larger tree that you've generated. Of course, these only have 500 nodes, so it's perfectly reasonable to expect that you'll see the remnants of the initial seed. So the question is, does this persist as the size of the network grows? Okay. So you can also run simulations with uniform attachment, and you see similar phenomenon. So here, if you started from a star, you'll see some kind of star shape, although this is perhaps less pronounced than in the case of preferential attachment. And also, you know, the central vertex of the star doesn't have such a high degree. And if you started from a path, then you'll see remnants of the path in your larger uniform attachment tree. Okay? So the question is, does the seed have an influence? So in order to answer this question, we first have to formalize what we mean by this. Okay? And there are various ways to do this. So perhaps the most crude way to do this is to just run the process indefinitely until you have a countably infinite tree. So then, because in these models, all the vertices, so any fixed vertex will eventually have infinite degree, so the limiting tree will just be the unique tree on countably infinite vertices where every vertex has a countably infinite degree. So this is not too interesting. In this sense, the seed has no influence, okay, in any such model where you see this behavior. But this is a very crude measure, although let me point out that if you do superlinear preferential attachment, which is kind of an extreme model, but where you attach with probability proportional to the degree raised to some power greater than 1. So it's a bit of an extreme model, but in that model, even in this very crude sense, the seed has an influence. Okay? But I don't want to talk much about that. Let me go back to preferential attachment and uniform attachment. So a much finer measure is to consider the weak local limit, or also known as the Benjamini-Schramm limit, which has come up multiple times over the course of this week. So there, what you do is, well, you have your large tree, and then you pick a uniformly random vertex, and you look at its local neighborhood. How does that look like? And, well, it turns out that the seed has no influence on this weak local limit in either of these models, preferential attachment, uniform attachment. So the weak local limit for preferential attachment trees was described by Rudash, Toth, and Balko, and later Jennifer and Christian, with collaborators Berger and Saberi, described the weak local limit of more general graphs, including these. So there, basically the idea is that the seed influences somehow the central part of the network, and the bulk, most of the vertices are only influenced by how the network evolves, not the initial conditions. Okay? But you can measure the influence of the seed in a much more finer sense, and I would argue that this is perhaps the most natural way to do this, because we do care about not just a typical vertex, but we also care about atypical vertices, so vertices that are somehow central in your network. So this is we can measure the influence of the seed via total variation distance. So this is the following. So suppose you run your preferential attachment or whatever process starting from any two initial seeds, S and T, for instance, the path and the star. And then you run it until you have a billion nodes for both. And then, so now you have two random trees on a billion nodes. These are unlabeled. So they live on the same space, same finite space of trees with a billion nodes that are unlabeled. So you can consider the total variation distance of these two distributions. And now you can take the limit as the number of vertices goes to infinity. Okay? This limit exists because it's non-increasing and it's also non-negative. So, okay, so this is our measure of distance. And what we're interested in is whether this limit is positive or is it zero. Another way of thinking about this question is as a hypothesis testing question. So behind my back, I flip a coin to decide whether I start the process from a star or from a path. And then I run the process until it has a billion nodes, and then I show it to you. And your task is to decide whether it came from a path or a star. Okay? And you can also flip a coin, and you'll be correct with probability half, but the question is, can you do better? And this is exactly equivalent to studying this limiting total variation distance. Okay? Is this question clear? And let me just point out one more thing, is that you can also compare two different seeds which have different sizes. So you can compare a star of size 10 and a path of length 5, just because you can run the process from either until you have a billion nodes and then compare them when you have a billion nodes. Okay?
So the total variation is monotone, you say, in N?
Right. Well, it's non-increasing because basically once you've coupled, then you can just run the evolution. Okay? Yes?
I presume that in terms of implementing such a thing, I don't know if any of these measures, and it's fine because I know this is, I know none of these measures are probably implementable. Is total variation somehow harder in some sense computationally if you were to do it than some of the other measures, or are they all about equally difficult?
Right, so total variation is the L1 distance, but on the space of trees, so it's you won't be able to probably compute it exactly, but there might be simpler statistics for which you can compute things, and which give bounds on the total variation distance.
So the emphasis in the work you described has been more sort of on what one can do in principle, and less on what might be realizable in some polynomial sense.
Yes, but the statistics that will be, you will be able to distinguish in this sense, and there are statistics that that you can run in polynomial time that will be able to distinguish. Okay, so I guess I've already told you the punchline, which is, in this sense, you do see an influence of the initial seed. In fact, in both preferential attachment and uniform attachment. So if you start from any two seeds that are non-isomorphic, and both have at least 3 vertices, this is just a simple condition I'll explain in a second. So then, the limiting total variation distance is positive. So the trees you grow, the random trees you grow really do depend on the initial condition. Okay, so what is this condition on the trees having at least 3 vertices? That just comes from the fact that, well, this is the only tree on 2 vertices that is unlabeled, and then if you attach another vertex, well, then this is the only tree on 3 vertices you can get. So you will not be able to, if you look at the path on 2 vertices and the path on 3 vertices, then you won't be able to distinguish them. Okay, but apart from that, so this is clear, but apart from this, you will be able to, you do see different limits depending on the initial condition. Okay? Okay, so initially we looked at this for preferential attachment, and we showed this under the assumption that the degree profiles of the two seeds are different. And then, in a very nice work by Curian, Duquesne, Korchemsky, and Manolescu, so they showed that this is true in general, just if the two seeds are non-isomorphic. And then we also looked at this and showed this in the case of uniform attachment. Okay? So in the following, I'll describe to you, how to do this, but first, let me ask you, how would you do this? Okay, in particular, suppose you want to distinguish a star of size 10 and a path of size 10 in preferential attachment. So if you want to distinguish these large trees, then you want to come up with some statistic that is different under the two. Excuse me?
Something on the degree difference.
Yeah, something along the degree distribution.
This matrix will be very different.
The highest degree point.
Yeah, let's look at the maximum degree. So that's very natural to think of because, well, in preferential attachment, you have this rich-get-richer phenomenon. So in particular, if you start the process from a large star, then the central vertex of the star has a high degree to begin with. So many vertices will attach to it. So it will continue to have a high degree, and it will continue to have many vertices attached to it, and so forth. So you can imagine that in the preferential attachment tree started from a star, the central vertex will have a stochastically higher degree than if you start from a path. Okay? So this is very natural, and this is what we did. And if you want to, so let me explain how this works. So if you want to understand the maximum degree, then you have to understand how the degrees evolve. And the degrees evolve according to Poya-Ernst. So maybe you've seen this already, so pardon me in that case, but let me just explain just so we're all on the same page. So if you look at some particular vertex I, then a new vertex can come in and it can attach to vertex I. This happens with probability proportional to the degree of vertex I. Or it attaches to some other vertex, and this happens with probability proportional to the sum of all the other degrees. In this first case, the degree of I increases by 1, and also the sum of all the other degrees increases by 1. And in this other case, the degree of I does not increase, but the sum of all the other degrees increases by 2. So this means that we have, so if you look at the degree of I and the sum of all the other degrees, then this is a Poya-Ernst with a replacement matrix 2, 0, 1, 1. So the two rows correspond to these two situations. Okay? And the initial condition of this Ernst process will depend on the initial seed in a particular way. And we know that Poya-Ernsts are sensitive to their initial conditions, so this gives us the heuristic that that here we should have a dependence on the initial condition. Okay? So just from the fact that the degrees evolve according to this process, one gets that they're on the, if any fixed vertex will have degree on the order of square root of n. And if you rescale by this, then you have some limiting distribution. Also, the maximum degree, denoted by capital delta, also scales by square root of n and has a limiting distribution. So this has been well studied by several authors. And what we try to understand is how does this limiting maximum degree depend on the initial condition. So in particular, we're interested in how the tail of this limiting maximum degree depends on the initial condition because, right, what we're interested in are extremes. And what we think is that the extremes will be affected by the initial condition. Okay? Okay, so what you see here is on the left, so this is the limiting maximum degree and the tail of that, and this is asymptotically equivalent to this expression here. So there are multiple factors here. So this decays rapidly, like e to the minus t squared over 4, but there's a polynomial prefactor, and the point is that this polynomial prefactor depends on the initial seed. Okay? In particular, in this power, you see the size of the seed and the maximum degree of the seed. So in particular, you see that if the maximum degree of the seed is larger, then this tail is a little bit heavier. Okay, it's not by much. It's very weak in some sense, this effect, but it's there. Okay. So in particular, if this power here is different for two seeds, then you can distinguish them because you can look at the maximum degree, and this will give you some power. It might be very little power, but it will give you some power. Okay. And from this, it's not hard to show that even if the degree profiles of the two initial seeds are different, then you can distinguish using the maximum degree. Okay. However, There are trees that have the same degree profile, but they're not isomorphic, so this is the smallest such pair. And in this case, you can actually couple the processes so that the degree distributions are always the same. Okay? So looking at just degrees won't give you anything if you want to distinguish preferential attachment trees started from these two seeds. Yes?
Can you, maybe you're going to say this, could you say a few words about where the bound comes from?
Where this comes from? Yeah, so basically you have to understand the evolution of individual degrees, and so this limiting maximum degree you can write as the max of all these individual degrees, and basically the max, so if you look at the tails, it will only be achieved by a single vertex, so you can use a union bound here. So you only have to deal with the evolution of individual vertices, and then so these evolve according to this Poisson process, and then there are very nice results describing the limits of those. Okay, so if you want to understand the difference between large trees started from these two different seeds, then you somehow have to incorporate some kind of geometry into your statistics. You want to understand the geometry of large degree nodes, okay? Because that is what will be different in starting from these two seeds. So we had some ideas on how to do this, and I'll just get to that in a second, but let me describe to you what Curie and et al. Did. So what they do is the following. So on the right here is your large tree of interest, and on the left is some small tree, it's some test tree, and what you do is you want to probe your large tree with the small test tree. Okay? So you can think of this as a test function in some sense. So what you do is you take this small tree, forget about these positive integer numbers on the vertices for a second, you take this small tree, and then you embed it into the large tree as shown here in bold, and then what you do is you take the degrees of these vertices, you multiply those together, that's essentially what you see here, and then you sum this over all embeddings. Okay? That's this sum here. So what's the idea behind this? Well, first of all, large degree nodes will contribute the most, because if you embed your tree to this statistic, because if you embed your little tree somewhere peripherally, then some of the degrees will be 1 if you embed 2 leaves. And then in this product, those will contribute a factor of 1. So the corresponding products will be on much lower order than if you embed this centrally, where all the degrees are on the order of n, the size of your, or whatever the largest degrees are. So really here, the embeddings where all of these vertices have large degree will contribute the most. Okay? But somehow, because you're embedding, you're really capturing geometric structure of large degree nodes by probing with some tree and not just understanding individual degrees. Okay? So one thing you can do is you can also put positive integers on these vertices and then raise the degrees to these positive integer powers, and this amplifies the difference between large degree nodes and small degree nodes. Okay. There's also a nice combinatorial interpretation of this statistic, but I won't get into that. That allows us to do the analysis very nicely. Any questions about this statistic?
Sorry, can you just, can you tell me, remind me what D sub T and I don't quite.
Yeah, sorry. Okay, I didn't want, so tau is your little tree, T is your big tree, and then you look at the degree of the embedded vertices, so you map U to phi of U, and you look at the degree in this large tree, and then essentially you raise it to this power of this positive integer. Here this is a falling factorial just because it's nicer for combinatorics. And then so you take the product of all these degrees, and then you sum this over all possible embeddings of this little tree into the big tree. Okay? Okay. So I'll get to how you can analyze this in a second, but basically what we were trying to do was look at, instead of a sum and a product, look at a max and a sum. So max over all embeddings of the sum of the degrees. so why we're thinking of doing that is because that's a direct generalization of the maximum degree, because then if you take a single vertex, then that gives you exactly the maximum degree. However, that's a bit harder to deal with, understanding the tails of that. Here, this is some kind of smooth max. Okay? And to understand this, you don't have to understand the tails, but it suffices to understand the first two moments of the statistic. So from this, the general framework is that from this statistic, you can construct a family of martingales, and for any two different seeds, there exists some martingale, so you look at some combination of these test trees to probe your big tree, and such that the expected value of this martingale is different at some time and then therefore for all times. And the main technical work goes into showing that these martingales are bounded in L2. And once you have this, then you can conclude using the Cauchy-Schwarz inequality that the limiting total variation distance is positive. Okay? So, okay, I won't go into details here. But so this concludes the fact that the seed has an influence in preferential attachment. Are there any questions about this? Okay, yes?
Martingales represent some kind of Radon-Nikodym derivative in some general sense, or maybe that has nothing to do with that? Just curious, because of the final statement there.
Sorry?
The conclusion that
oh yeah, so I mean this is just, well, if you have some random variable that, right, the means are different, and you're bounded in L2, then you have a positive total variation distance. Okay. Okay, so let me go to uniform attachment. Well, and what's the difference? So in preferential attachment, so let's look at these two seed trees, S on the left and T on the right. And if you look at this central edge and these two vertices on the left and right, then here in S, the left vertex has a larger degree than the one on the right, so it has a head start and it will be stochastically larger. Under preferential attachment, these two vertices in T have the same degree to start with. They will have the same degree going forward, well, the same distribution. In uniform attachment, the degrees don't matter. So just because this guy on the left has a head start, it won't matter in the long run. Okay? So what can we do to look at some other types of differences? It turns out what you can do is you can look at the subtree sizes on either side of this edge. So if you look at this central edge, the subtree sizes on the left and right in S have size 6 and 2, and in T they're equal. They have 4 and 4 vertices each. And now how do these evolve? Well, it turns out they evolve according to the classical Poya-Ern, right? Because if a new vertex comes in, it attaches to the left subtree with probability proportional to the size of that subtree. And it attaches to the right subtree with probability proportional to the size of that subtree. Okay? So this is just a classical Poya-Ern. So if you look at the normalized size of the subtree, the left subtree, say, then in S it will be beta 6,2, in T it will be beta 4,4. So they're different. Okay? Now, if you just get a large tree, you don't know which edge to look at, so that's the difficulty. But this is the basic idea behind why the seed has an influence in uniform attachment trees, because of this balancedness property. Okay? Okay. So let's look at this quick example, simple example quickly. So suppose you want to distinguish a path of length 4 and a star of size 4. Then you can look at the following statistic. So you look at a particular edge, and then you look at the sizes of these subtrees on either side of the edge. You can multiply them together, and you can normalize them and raise it to the second power. That's just for simplicity. I'll get to that in a second. But basically, you multiply the subtree sizes together. And then you sum this over all edges, because you don't know really which edge you should be looking for, so you sum this over all edges. And again, the idea is similar, that central edges will contribute the most to this statistic, and peripheral ones won't. So if you look at a central edge, then, well, the subtree sizes will be roughly equal. So this quantity will be on the order of 1. It'll be constant. On the other hand, if you look at an edge that is peripheral, so it's adjacent to a leaf, then one of the subtrees will have size 1, the other will be n minus 1. So this quantity will be on the order of 1 over n squared. Okay? So it'll be small. Okay. So if you want to distinguish uniform attachment trees run from either of these two initial seeds, then basically what you can do is you can look at this statistic, and what you have to show is that the means are different and the variances are finite of this statistic. And so this can be done simply. I won't go over this in too much detail, but I just want to show that this can be really, it's a simple computation. So if you look at new edges that come in later that are not initial edges, then, well, when they come in, they initially have if you look at that edge, then initially you have one of the subtrees has size 1 and the other has size whatever it is. So these will behave the same no matter if you look at you look at the process started from either seed. So this quantity will have the same distribution. So if you look at the difference of expectations, those will cancel out. Also, if you look at this edge in the path and this edge in the path, E1 and E3, then those will behave similarly to any edge in the star, because initially you have on one side you have one vertex and on the other side you have 3 vertices. The only difference is this central edge in the path, initially you have 2 vertices on either side, and that's something you don't see in the star. So basically the difference in expectations of the statistic boils down to this difference of this simpler quantity for this one single edge. And this evolves according to a Poirier. So basically, you only have to compute some moments of some beta binomial. This is pretty simple. And you get something that is non-zero. Okay? And for the variance, you can use Cauchy-Schwarz. And that's why I put the squares on that statistic, because then you can use Cauchy-Schwarz and you don't have to worry about anything, about any correlations or anything. And again, you can just use estimates on moments of the beta binomial, and you're good to go. More generally, so this statistic will distinguish many different seeds, but it won't distinguish all of them. And to distinguish all of them, you can look at more general statistics, just like before. So, but now, again, you're probing your large tree with smaller trees, but now, instead of multiplying the degrees together, you're multiplying the subtree sizes together. Okay? And again, the idea is this captures some kind of global balancedness properties of the tree, and embeddings that are central contribute the most to this statistic. Okay? Okay. So the general framework is similar. You can build martingales from this, and the main technical difficulty is to show that these are bounded in L2. There are some additional difficulties compared to the previous case, just because these statistics are, these subtree sizes are non-local, so those pose some additional difficulties, but they can be dealt with. Okay. So this concludes the fact that the seed has an influence in uniform attachment. So now I'd like to move on to the second question, which is more estimation. So the question is, so we now know that the initial condition has an influence on the large tree. The question is, can we estimate the initial condition? And if so, can we find it? So now I'd like to focus on the simpler question of, suppose you know the seed, and suppose you know that the whole process started from a single vertex. Okay? Then can you locate that in your large tree? So you won't be able to locate it exactly. But what you can do is you might get some small subset of the nodes and have guarantees saying that you will be able to find the initial root, within this subset of the vertices. Okay? So in particular, we'll say that something is a root finding algorithm if the following holds. So you have some large graph G with n vertices, and you have some error probability that you're gunning for, epsilon, which is between 0 and 1. And what you want to output is a set of vertices H that, it can depend on this graph in epsilon, but the size of this set H does not depend on n, it only depends on epsilon. Okay? And what you want is a guarantee that the root is within this set with probability 1 minus epsilon. Okay? So I want to be 99% confident that the root is within the set, but I don't want this set to depend on, I want this set to be of some specific size, even if the graph has a billion nodes. Okay? So because of this definition, it's not obvious that such a root finding algorithm exists. In fact, there are some cases when it doesn't. But it turns out that root finding algorithms do exist for preferential attachment and uniform attachment trees. This is work of Sebastian Boubec, Luc Devroy, and Gabor Lugosi. And so once you know that these exist, then a natural question is to understand what is the smallest size set you need to output for which you can have this guarantee. Okay? So it turns out for preferential attachment, this will be polynomial in 1 over epsilon. Whereas for uniform attachment, there are bounds that show that it's subpolynomial in 1 over epsilon, but it's super polylogarithmic in 1 over epsilon. Okay? Okay. So this, at first, actually might seem counterintuitive because preferential attachment seems like, you will be able to nail down the root better there. But the point is that, if something can go wrong at the beginning. Okay, it might happen that at the beginning, just with a constant probability, you start from a root, and then really the graph evolves somewhere else, and this becomes the central part of the graph, and then preferential attachment amplifies this, so the root will really get lost. So basically, in preferential attachment, if something goes wrong, then something goes very wrong. Okay? And that's not the case in uniform attachment. Things are more mellow there. So that's the reason why for this result. And so we also looked at uniform attachment when you add m edges at a time. And it turns out, in this case, root finding algorithms do exist. And the size of these sets are much smaller. They're essentially on the order of log 1 over epsilon up to polylog factors. So the takeaway from this is that extra edges do help in locating the root. Okay. So what I talked about so far is all about a graph growing, a network growing, and understanding where it came from, understanding how to find the root, and so on. But often we don't just care about some underlying network, but we have some processes evolving on a network. So in particular, lots of times you have some kind of information propagating on a network, and so say a rumor, and you could be interested in finding the rumor source for various reasons.
So the topology is fixed.
Say the topology is fixed for now. Yes, of course, in practice one would like to understand how these co-evolve and so forth. But for now, let's fix the topology, and there's some rumor spreading on some fixed network, and we want to understand, can we locate the rumor source based on knowing the graph topology and how the information spreads, and also which vertices are infected. So there's been lots of work on this, and I won't mention all of it. Basically, I'd like to mention this paper by Shah and Zaman, who introduced this notion of rumor centrality, which has been pretty influential. And the general theme is similar, that the rumor source can be identified reliably if you look at traditional diffusion models. So, some kind of exponential clock ticking at each node, and so on. Okay, so there's been lots of work, and so sorry if you in particular have worked on this, and but okay, so it would basically you could give a whole talk on just all of this work. What I'd like to look at and tell you about is a twist on this story. So, is there any way to obfuscate the rumor source? And this in particular has become relevant with because people do want some kind of anonymity, and in some applications it's very crucial that the only way people can really spread information is if they remain anonymous. Otherwise, they will not want to, or they will have severe repercussions. So there have been several anonymous messaging applications that have come up recently to try to solve this problem. And so the question is, can we hide the source of the rumor? And what you can do is here you have the power to come up with how the information spreads. Okay, so you are in charge, and you can really define the diffusion protocol. Okay? And what you'd like is that the information spreads, and it spreads fast. But moreover, you would like the source of the rumor to remain anonymous. So ideally, you would like perfect obfuscation, which is that given that you see which nodes are infected, the maximum likelihood estimator for the source, well, it puts only like roughly 1 over n mass on the source. Okay, so roughly all vertices are equally likely to be the source. There's very nice work of Giulia Fanti and collaborators recently that introduced what is called adaptive diffusion. And I guess I don't have too much time to go into this, but maybe I could tell you offline. But basically, it's a way of spreading information that it has various nice properties. In particular, if you look on infinite regular trees, then it does lead to perfect obfuscation, and it leads to order optimal rate of spread. So by this I mean that the spread of how the speed of information propagation only slows down by a factor of 2, as opposed to if everyone was always propagating the information instantaneously. Basically, the idea is that you go in a random direction away from the source and spread the information along there. Okay? It's not just this. There are several tweaks to this that make it even nicer, but I won't go into this right now. What I'd like to tell you about is, well, is ongoing work with Jacob Ritchie, who is a grad student at University of Washington, is that, so this is very nice and it has lots of desirable properties, even for not regular trees, the irregular trees, even for graphs that are not trees, and even you can via simulation understand the performance for real world graphs, and it does very well. But it doesn't really spread the information locally. And often you would like to spread the information locally, right? Because if you're in Tahrir Square and you want to spread some sensitive information to your friends, you don't care if the information spreads all over North America. What you really care about is that the information spreads within your community in and around Tahrir Square. But of course, this goes against source obfuscation, right? Because if all of your friends know about this, then, well, you might be likely to be the rumor source. So what's an interesting question is, what are the trade-offs between locally spreading information and source obfuscation, preserving anonymity? So what you'd like to do is really have the information spread locally, and maybe you're willing to give up some amount of anonymity. Okay, so you don't want perfect obfuscation, the maximum likelihood to give a 1 over n mass to the source, but maybe it's okay if the maximum likelihood is correct with probability 1 over square root of n, or something along these lines. So we have some work in progress that you can achieve some trade-off between these two, but the question of the optimal trade-off is still open, and this is something we're working on. So let me just, in the last minute, summarize. So I hope I've convinced you that the initial condition, the initial seed graph, is important in the evolution of networks. So we've seen this in the case of preferential attachment and uniform attachment trees. And we've seen that degrees in preferential attachment play a special role. Of course, This is not surprising. This is well known. In uniform attachment trees, this notion of balancedness played a key role. And we've also seen root-finding algorithms. So a general open question is, how robust is this phenomenon? How wide is this phenomenon? And my guess is that this is a pretty universal phenomenon, that the initial condition will influence how graphs look in general for much more general models. And it's worth studying, how for other models can you show something like this. On the other hand, a flip question is there any natural model where the seed has no influence? Okay. Then there are various questions of estimation and finding the seed, which are very relevant. And at the very end, I told you about trade-offs about rumor source obfuscation and various trade-offs between anonymity and locally spreading information. Thanks for your attention.
So, there are questions for Miklos? You already asked a lot, so.
I do have one question. So you talked about two different growth mechanisms that could be related in a nice general framework. Have you looked much at other powers?
Oh, yes, that's a good question. So if you look at sublinear, so alpha between 0 and 1, that's very natural to look at. And so I looked at it a little bit. I think basically the same statistics should work. Analyzing them is harder because you don't have this nice combinatorial structure. Basically, the main technique that you can use is embed the graph growth process into branching processes, and you'll have to understand how various things behave there. And there is work done there understanding limits of will be Crumps-Jaeger's branching processes. But so you really have to understand the limiting random variables you get there, and there's lots of things known about them qualitatively, like they're bounded in L2, they're almost trinally positive, they have a density, and so on and so forth. But to understand the influence of the seed, you really have to get more quantitative results.
And if you let out
But
the power vary across time,
across
the
time.
point where you had the smallest or the highest value take over, or it just get very complicated and you couldn't think about it?
It's not clear.
Okay.
That's a good question.
So let's thank Miklos.